which is David Pichardie from Meta. David is known worldwide for his work on abstract interpretation, on work with proof assistance, in particular ROC, and in particular the combination of those two. He was one of the first to actually do what we call certified abstract interpretation here. So he has a PhD and a habilitation here from the University of Rennes, where he was first working as an INRIA researcher and then as a professor at INS Rennes, and now as with Meta. So over to you, David, and for about 45 minutes, 50 minutes of talk.
Okay, thank you very much. Thank you for the program committee for inviting me. It's a great honor. It's also a great honor to present the state of this great project, Infer, which has been here for more than 15 years now. I play at home today because I work from Rennes, full remote. And yeah, I will try to present what is Infer, what are the current state, and I hope I will give you a better understanding of this project. So the first best way to start is to give a demo, or mostly a demo because it will just be on slides. So imagine you have two Java files with two functions in each file, and okay, you want to check if there is something wrong. You ask Infer, and Infer will tell you there is something weird here. And the kind of reasoning that Infer is doing is really interprocedural. So behind the curtain, what Infer is doing is understanding that the first call to foo is going to this function. Infer is understanding that in this function you will call another function which will return null and set your A field to null, so that when you go back and call this function, here you will dereference a null pointer. So this is really a reasoning about interprocedural steps, okay? And Infer is really trying to follow all your call graph edges and give you some very actionable signals. Today, what I would like to explain and present is what in my opinion, make Infer a success in industry, and what make it a singular point in terms of design choices. So I will try to focus on very specific features, mainly 3 of them. The first one is that we have a common IR to all the front end we support. So there is a big work around intermediate representations in this project. The second point is this motto that we can start from anywhere. I will try to explain a bit what it means. It is related to the specific interprocedural technique we use here. And at last, I will explain a bit why and how we try to favor false negatives over false positive, because we really care about the quality of the signals we send to developers. So, but first, because now it's an old project, I want to spend a few minutes explaining a bit the history of this project, because many of you are too young maybe to know that, but you need to know about this story. And you can hear me, but at some point you will also need to read this article by Peter Owen, where all this story is well explained with far more details. It is the CACM paper. So, in a sense, it all started with Tony Orr, because Tony Orr presented this idea of Orr logic to prove correctness of programs. When you go back to this time, it was quite a theoretical contribution about giving semantics to programs. And still, there is a clear link with what I will present today. So it's a first, I think, amazing point. A major step a few years after was about inventing a logic which reasons well on pointers by Peter Owen, Reynolds and others. So separation logic was also a great milestone for the Infer story. At that time, even if programs looked a bit more realistic with pointers, it was still quite a theoretical contribution because it was hardly believable that it will scale, because you still have to annotate all your program with pre, post, loop invariants. So scaling to millions of lines of codes was not clear. And this is what Peter and his colleagues focused on a few years later. So they invented this notion of B-abduction, which is really a way to infer all these annotations that program logics require. And the first experiments proposed by this paper were really encouraging. They were analyzing a Linux kernel, for example, at this time. And I think at this point it was clear that there was a clear potential for scalability. They were also very motivated by having impact in industry and real life. And they founded, 3 of them founded a startup, Monoidix, 2009. And 4 years later, yes, the startup was acquired by Facebook. So extremely quick process. They were invited to give a demo at California HQ. They analyzed Facebook code there. And 1 week later, the deal was done. So very impressive movement with announcement in newspaper. And yeah, in 2026, Infer is still there. The company is named Meta now. By the way, it's an open source project, so it's not only for Meta. And yeah, every day at Meta, people submit what we call diff, which is kind of pull request. It goes to an environment, a CI, named Fabricator, also a nice open source project. It goes to the continuous integration, yes. You need a human reviewer to accept your pull request, otherwise it will not be landed. But there is also another tool in the loop, Infer. We will check your code. And it is happening every time, every day. It's happening now. Okay. And yeah, it's really an example of scaling to industry. If you look at the numbers, we have thousands of developers in this company. They maintain, develop more than 10 of millions lines of code, far more. And we have hundreds of code changes per day. So we need to go fast, we need to scale, and we don't want to waste this developer time. Okay, that's why I will mention false positive and false negative in the last part of this talk. So for me, the first learning outcome of this nice story is first, principal research can be impactful. It can take a bit of time. Okay, you start from Tonier. But at the end, I think Infer is a real example of impactful research that is born from this community, programming languages, static analysis, semantics. So maybe you can reuse some of these slides in your course or examples when you want to explain to people why you are doing your research. Okay, now the first feature I would like to explain, is this notion of common IR. So if you are familiar with LLVM, this is something a bit similar. This picture looks a bit like what LLVM is, but Infer tried to do the same for static analysis. So we have one common IR at this center here, and we translate many source languages to this IR, and all the analyses share a common analysis platform. You will have more details in the rest of the talk. I will also mention that all these front ends do not have the same maturity. Some projects are still ongoing. But there is really this idea that we don't develop a new platform for each time we want to analyze a new language. And in a company like Meta, you really need this flexibility because you will have to adapt to new languages. Okay, the new languages will come, and hopefully you will be able to adapt your static analysis platform. Just to mention, in this talk, I will give you a lot of details about the core elements of this platform. I will not mention so many examples of analysis because you will see that from these core elements, you can develop a lot of different analyses. Okay, let's zoom a bit in. So we have all these front ends, and they will all be translated to a same intermediate representation, named SIL for Smallfoot Intermediate Language. So Smallfoot was the first name of the tool before Infer. And then we have the backend analysis, where we use a lot of well-known academic techniques, abstract interpretation, incorrectness logic, SMT solvers. And all this analysis can reuse some of these elements, maybe not all elements, but some of them, to do their own work. And sometimes one new analysis is really a small configuration of this element. You don't have a lot of work to do for your new analysis. So I want to start by giving more details about this IR. So in 2022, we managed to renovate a bit this IR because there was a need, because it was not so easy to emit this IR. So every time we wanted to add a new front end, the workload was a bit high. Indeed, this IR was not meant to be written by humans. It was really meant to be used by analysis tool. And we wanted something cleaner, easier to manage, to emit, and also easier to understand. The project was already old, 10 years. So this new IR here, which is named textual, because you can really see the text representation if you want. You can adapt it just a few characters and re-emit them to the analysis if you want, a bit like the LLVM bitcode. So yeah, this idea is that we want to facilitate addition of new front ends, and we want to better understand the intermediate representation. So indeed, after 2023, all the new front end were directly based on this new representation. So, so the last two are work in progress, Rust and Swift, which go through LLVM. There will be a nice talk today about this new front end. And some recent front end about Python and Hack, which is a typed version of PHP. Were directly using this new IR. So this is an example of program in this IR. Very factorial, of course. You need to give an example with factorial. So a module is composed of function, type declarations, and prototype declarations. This is just an example of function. A function is a control flow graph with blocks. Each block has a name. A block is a sequence of instructions, and it ends with a terminator instruction, like in LLVM. A terminator can be a jump to several successors. And inside the block, you can use the prune instruction to constrain the current instruction. And the semantics is that you are stuck if the Boolean test is false. Okay, so it's very standard, I would say. But it is really a language. It has a syntax. You have some tools that help you write some well-formed programs. There is a type system. We will catch many errors. And there is also an inference type mechanism so that you don't have to write all the types yourself. And some high-level construct, like you can declare a closure, if you want, inside an expression, and it will be transformed with the right encoding later. So yeah, you can emit a lot of code easily with this new language. And we have algorithms to transform, compile, all that into the old internal representation of Infer. Okay. And yeah, in terms of impact, it was quite successful in the sense that we were able to mostly develop a new front end each year. So we were really happy with this new IR. And yeah, it's really a core language. So all the languages here. This is the OCaml abstract syntax of this language. So it's, in my opinion, really amazing that you can turn all these complex, realistic source languages into one common IR and just try to reason on it. Of course, it is not that easy, but if you think about it, it's a great lesson. This is my second lesson for today. You need to remember your compiler courses. It's amazing what you can do with a good compiler technique. And LLVM is a super cool example of that. Of course, I don't want to give you only the good story. Of course, it is not that easy to have one common IR. So it's a matter of trade-off, of course. Of course, all the backend analyses are not completely independent of the source languages. You sometimes have to check what is your source language. So in some places in the analysis implementation, you will see some tests like, if I am analyzing Java, then. Okay, there is no free lunch, but still many parts are shared. Of course, second point, is not that easy to compile to a single, simple, intermediate representation all the modern languages ahead of time. Think about Python, for example. So if you look at the Python front end currently in Infer, you will see that so we have only 4 instructions in this core language. Okay, store, load, the prune I have presented before, and a let, which is a way to do some calls. And in Python, we just emit let because everything is thrown to a built-in call. And later, each analysis will have to understand how to interpret this built-in. So this is still a common IR, but in fact, we do not share so much at compile time. During analysis, we have a way, I will not present that today, we need another talk. We have a way to reuse a lot of the common architecture when we write the transferred function for each built-in. So it's still there is still a lot of reusable work. But yes, there is no magic weapon. Compiling ahead of time modern languages is not that simple. Other points, there is a famous motto in static analysis. Analysis source language enable more subtle abstraction of high-level features. So if you think, for example, about Astray, was a very successful industrial scale static analyzer. It works at very high level, very close to C. So Infer took a bit the opposite direction. I think we partially mitigate this problem thanks to the highly symbolic abstraction we use and the highly precise heap abstraction we use. And you can also look at Mathieu Lemaire's work, where he explained well what symbolic execution abstraction, how it helps you to recover part of this problem. But yeah, we are a bit at the extreme of the line around this choice. And so yeah, at the end, I think it was really a winning trade-off. And it's not only about science, it's also about engineering cost. So if you have a new engineer coming to your team, maybe this person is not a PL expert, he will be able to reuse a lot of elements. He will see a very simple language. So he doesn't have to be an expert in Swift, Java, or C++ immediately. So I think the learning curve is also very interesting in terms of engineering. And as a PL enthusiast, I must say it's so cool to be able to deal with all these languages in the same platform. So myself, it's really a pleasure. Okay, so it was for explaining a bit the state of this intermediate representation. Now let's talk a bit about static analysis. So in fact, after emitting this IR, we go through an AI framework where you can plug many abstract domains. Today, I will present a bit the AI framework, and I will also zoom on this specific abstract domain named Pulse, which contain incorrectness logic and SMT solvers. But first, a bit of AI framework. So some parts are extremely standard. The intra-procedural part is really the textbook abstract interpretation approach. You have this notion of lattices, this notion of transfer functions, join, widening. We are working on the control flow graph, remember, so we need a good iteration strategy to find the fixed spot. So we use the well-known technique named Bourdoncle strategy, using graph algorithms. So yourself, if you just want to write a new intra-procedural analysis inside Infer, you just need to open a simple textbook and implement very basic operators. So it's very simple. The interprocedural part is more tricky. I think static analysis experts in the room will acknowledge that this is the hard part. Scalable interprocedural analysis is really hard. I will not claim there is only one solution to solve this problem. I think Infer is solving part of this problem, and it is solving it very well, taking into account its own industrial constraints. So what we use is this summary-based compositional analysis technique that I will present. We use parallel computation to traverse bottom-up the call graph. And we perform an on-demand exploration so that we don't need to build the call graph first. So let me give a bit more details. I'm not sure everyone is familiar with the interprocedural landscape, so let's switch to a crash course about that. Imagine this is a control flow graph. Each box is a function, and a function is calling other, and so on. If you start, okay, you know how to do an intra-procedural analysis, and in your control flow graph, you have goto, you have jumps. So maybe you can already do that interprocedurally, why not? Indeed, you can. This is what we will call naive context-insensitive analysis. And what will happen is that when you go here, you will join all the colors states, and when you will jump back, you will use the context that is at the end of this function. So you will merge a lot of context. You will also invent paths that do not exist, indeed. So it's extremely simple design. Mostly you can just reuse your intra-procedural framework if you want, but do not hope for a lot of precision doing that, because you will, for example, you will invent a path like I jump here and I return here. So this invisible path, which is considered by this analysis, it will lead to a lot of loss of precision. So very scalable, can be very quick, but don't expect a lot of precision here. If you want better precision, you need to be context sensitive. So now, if we name a bit the calling context, we will analyze this box 2 times, in a sense. We will analyze it with a context 1, and this context will, and this color will benefit from this specific analysis. And we will reanalyze, in a sense, this function another time and benefit from the specific context here. But we have to continue like that. So here you have a multiplications of contexts. So you have more and more context to consider. So at the end, you gain a lot of precisions, but scalability is far harder. And if you look at the big picture, to do such an analysis, you really need to take into account cyclic dependencies, because the callee depend on the color context to know how with which information to start its specialized analysis. And the color, of course, depends on the callee analysis result. So these mutual dependencies has very bad consequences also in terms of scheduling your analysis. And most of these techniques are used in a setting where you need to know where are the entry points of your program. So if it is a big web page for a social network, for example, I don't know, you have many entry points, very complex, and you need to start your analysis from there. Okay, you cannot start from anywhere. You can still use this notion of on-demand. There is a literature about that. You can try to be a bit lazy, of course. But this is not exactly the same setting that the next technique, which is compositional interprocedural analysis. So here, the main tool is this notion of summary. So for me, a summary, it's a big formula that represents the behavior of an individual function. So it's like a book filled with formula. And this formula is expressing the behavior of this function, but without any assumption about the calling context. So it means you can start this analysis even if you don't know what are your colors, okay? And then once you have these books, you can build this summary here, and you can build this summary and so on. So in this approach, you really want to be able to start from anywhere. You have removed one important dependency because now the callee does not depend on the caller. So it will also help with the scheduling. You can use dynamic programming, in a sense, to perform the global analysis. In fact, we don't do that because we still want to be a bit on demand and only analyze the functions that looks necessary for the current fragment of code we analyze. And in theory, you should only have one summary per function. And this summary will be used by all call sites. So this is a compositional approach. A demo, you start from this function here, hey, and you call B. So you don't know who is calling A.f, you don't care. You want to build a summary for F. You see a call to J, so you jump to J. You see a call to H, and here H, imagine you don't have calls anymore. So you can build your summary. You store it somewhere. Maybe it will be reused later by others. You go back. Same for function E. You build a summary. And when you reach this point here, you can reuse this call. You apply the formula in this context. And if your logic is expressive enough, you have a very expressive formula in your calling context. And you can go back. So this is really what we call on-demand. This is not the full bottom-up dynamic programming approach. We wait for having a proof of need to perform a summary computation. But we only build one summary per function at maximum. So it's linear in the number of functions. Okay, but in this previous example, all the calls look so simple. Static calls, it's very simple. The name of the callee, it's written there. And you must know, if you program in modern languages, that is not that simple in real life. So think about virtual calls. So this is a virtual call to method M, but who is M? To understand who is M by the object-oriented approach, you need to know what is the object O, what is, how was it constructed, what is its runtime type. So this is a very implicit call. This is not a static call. You can have closures. So this is a closures with a very nice syntax of Objective-C. So for me, it's always a pleasure to write this syntax. You apply. This is you have one parameter, and this parameter is a function of type integer to void, and you just apply it to 0. But you don't know what is this f. You need a value analysis to understand who is really called here. Another well-known example, function pointers. You don't know what function will be called exactly here. This is a pointer to a function. And in a recent work around PHP hack, we also have this beautiful notion of let static binding. So there is a lot of static calls in PHP, but in fact they are not so static in a sense. This is me explaining this notion. So yeah, again, a very implicit call, and you have to deal with that. And what I found very nice with the current approach we had in Infer is that first, we translate all this notion to a single notion of implicit call, which is mainly virtual call. We choose virtual call to represent all these notions. So using compiler techniques, we translate all this notion into one, and we try to have a very robust technique for virtual calls. Let me explain. So what happened with virtual calls is you have all these callers, and they call function foo, where there is a very implicit call. You don't know which M is called here. So what you could do, a naive approach, would be, okay, let's imagine I know all my code base. I know all my class hierarchy. So if I have a good type system, which sometimes I don't have with the modern languages, but imagine Java, for example, I can look at the static type of O, and I will find another approximation of all the potential callees. Then I can make a big union of all the possible behavior. But good luck with the size of the summary here. The summary will probably be extremely big. And in practice, at runtime, think about Python, you probably will use very few of these callers. So it's really a waste of resources because you are joining a lot of potential behaviors, while in practice you only use very few of them. So we don't want to do that. And to address this problem, we change a bit the way we use summary in Infer. We introduce this notion of summary specialization. So there will be another talk today about that in the same workshop, TPSA workshop. And yes, so summary specialization, this idea is that, okay, we will allow a function to be analyzed several times, but for various specialization keys or calling context, in a sense. So it's really a mix between the two context-sensitive interprocedural techniques I have presented before. If you think about virtual calls, the information you need for specialization is really related to runtime types, okay? And we will ask the caller to give us a specialization key. So let's just give you a demo again. We start with function f, which is really nice because it only has static calls. Then we jump to b. We want to build a summary for b.j. And okay, this is a static call, fine. But when we go here, we see a virtual call. And to resolve this virtual call, we need to know what is the dynamic type of x. And we don't know. X is a parameter. So we stop, in fact, this summary construction. And we go back to the initial caller and explain that it will require some extra information. And if the caller has this information, for example, imagine here we know that y is of type C, we can send this information, and now the call here will be resolved. So it means we will build and store a specialized summary which contains an assumption about the parameters. If you are lucky, you will be able to reuse the summary. If you are not lucky, the next time you call G, you will use it in another context and you will need another summary. But you will do this process on demand. So you will only analyze a function with a specialized summary if there is a proof that you need this summary for your analysis. So it's even more on demand than before. Okay, so we have introduced this approach in 2023. As I will mention, these days we use a lot incorrectness logic, and this approach is far easier to understand and implement in incorrectness logic because at some point we can give up, in a sense. So if we run out of resource for building new summary again and again, we can just stop and cut the exploration. This is what incorrectness logic allows to do. So in practice, we have to bound the number of specialized summaries. We analyze more code than before, so there is a time overhead, but there is also a clear expressiveness win with respect to all these implicit calls I have mentioned before: closures, virtual calls, let static binding, and so on. And what is nice is that if you know a bit about separation logic, you know that there is also some difficulties with aliases context, because during the construction of a specific summary, you will have to assume that some parameters are not aliased. In fact, it's an assumption, and maybe at the caller side, you will detect that this assumption is false. It's not a problem. You will reanalyze the same function with the alias specialization key, explaining that this time you want to assume that these specific cells are aliased. So it's nice that with the same setting, we are able to express very different notions and limitations. So third learning outcome, be compositional, in the sense that it's really interesting to have this compositional interprocedural approach interprocedural. You can start from anywhere. And it has this advantage that I call air pockets, because sometimes when you develop an industrial scale tool like that, maybe you will not have access to all the code base, for example. So some callee, you will not know them. You will have to skip something. So being able to skip in a compositional way a call is really interesting and I think important for the design. Maybe you will run out of exploration budget also, so you have to stop and you have to skip this call. Or maybe you have to deliver a new front end, a new analysis, but you are not completely done with all the features of your language, and you can just model some call very badly. But there is no free lunch again. I don't want to hide details. It's not so easy to have a good notion of summary. You need a good and expressive abstract domain to be able to express a formula about post and precondition. Because remember, you do not assume anything about the calling context. So it means you really need a relational abstraction about the pre and the post states. And in Infer, because most of the techniques are based on separation logic, we will not only need to reason on these pre-post, we will need to infer them. Not only the post, but also the precondition. And this is really what is explained in the B-adduction paper I have cited before. And very recently, yes, we introduced this summary specialization technique to inject a pinch of call site information. And if you think about the compiler world, it's a bit of partial monomorphization that we do, because all the examples I have shown before were very polymorphic functions. Okay, so this is the AI framework, intra and interprocedural. Let's jump to the pulse domain. So yeah, I will try to do that in 5 minutes. So this is a very important domain for us. It has been developed recently by Jules Villard. So the idea is really to replace the whole B-abduction engine that was used in Infer. We want to be very strong and very precise with pass sensitivity, because you can have a lot of false positive if you are not very precise with pass sensitivity. Coming from separation logic, we are extremely we want to be extremely good with memory reasoning, and we really want to favor false negative over false positive. I will explain that later, but this is really a new re-implementation of the B-abduction approach, but with this bug finding approach. The goal is to send signals which have a highly chance to be true bugs. So, crash course on pulse. First, you need to understand a bit what is a symbolic state. So, in a symbolic state, imagine you have something like that at each program point. You will have a notion of symbolic value. So this value is a set of symbols, fresh variables. You will attach such value to program variable, the names that were already here in the source program. And they represent the address of this program variable in the stack. You may also have some logical variables that have been introduced by the compiler, but you will not see them in my examples. And then there is this classical notion of points to in separation logic, explaining that this address points to a cell containing this value. Okay. And we can attach a lot of attributes to all these symbols, depending on the specific analysis we want to do. This is the part that is really configurable and that we adapt every time we need a new analysis. And imagine you just have this C statement to analyze. So you assign the field. You will need this precondition and you will need this post condition. Yes. So here we are explaining that we have named Vx the address of program variable x. When we dereference Vx, we find another symbolic variable VL. And VL, if you consider the offset next attached to this address, you point to Vn. And if you dereference Vn, you go to V0, and V0 is invalid. So we have many points to predicate used in this very simple example. Yeah, I don't know why it is animating. But this is just the base domain. And in fact, what we will infer and propagate at each program point is a triple of one precondition, one post condition, and one pass condition. Pre and post belongs to this notion of base domain. But we really want to infer the precondition of the current function. So we will, when we perform our intra-procedural abstract interpretation, we manipulate a triple here. And the pass condition, we are accumulating all the assumptions, all the prune statements that you have seen before, the assume, in order to have a formula constraining the current pass. So this is a full example of a function foo, where L is a pointer to a list, and we do the same assignment as before. When we will start the abstract interpretation, we will start with an almost empty state. Here we are just declaring that, oh, okay, it should be x, sorry, that x is a valid parameter. And after one step, we have inferred that, in fact, we need a bit more assumption about x. And we have also inferred that after this assignment, the content of this field is not a valid address. Okay? And every time there is a call, every time there is a prune, we'll try to check if some infeasible path has been detected. Okay? For that, we use the well-known notion of SMT solver. We have our own SMT solver inside Infer. We choose a very decidable fragment of theories. We have a conjunct of ground terms. We use a Shostak combination of basically the two theories, congruence closure and linear rational arithmetics. Of course, a bit of integer reasoning or nonlinear arithmetic is always good to have, but we want to keep a very cheap approach. So basically, we use some interval arithmetics to do that. And this is our own solver. It is incremental, meaning that every time you do a step, you just do a small modification of the current state. Everything is programmed in a functional way. So we have a lot of sharing, and this sharing in memory is really important for scalability. Especially because, in fact, what I have just shown is just one state, but in fact, we have a disjunct of state that we manipulate. So at the end, we are really doing a partial exploration of all the paths inside your function. Of course, we need the limits. Incorrectness logic explain what this limit means. And sometimes we just unroll some loops if we cannot find the invariant after a few iterations. Yeah, and what is nice is it is not just symbolic execution, because we have this very specific interprocedural technique to compose summaries. Okay, and to conclude soon, the outcome here for me is that signal quality really matters. We cannot afford to send too many false positives to developers. Their time is very precious. And we are not in an industrial setting where we will have 0 alarms soon. Okay, so it's a trade-off. In our setting, we want to make sure that at least 50% of our signals are taken into account by developers. If a specific analysis is below that, we will not use it in production. And with all this approach, here you have example of 3 recent analyses we have performed using Pulse and the recent front end for Hack and PHP. And you see that the fixed rate are around 50, 80 and 77 fixed rate. Yes, so it's quite good for our standard. So to conclude, it's quite amazing that after 15 years, Infer is still delivering this impact at scale in industry. I promised to explain 3 features, but in fact there was 4, because I think the first one is foundational programming language research matters. Remember that. This compiler approach also is really interesting in my opinion. Compositional interprocedural analysis was really a winning approach for this specific setting. And the recent shift to incorrectness logic was also very important, because the false positive problem is really something specific companies cannot really afford, in a sense. So altogether, this is the end of my talk. And yeah, you will have other information today about the ongoing front end for Swift. Yesterday there was a talk by academic collaborator Andrea Costas explaining there is an ongoing project to add a Rust front end. And we have some ongoing project or of course brainstorm about how to ride the AI wave. I will not detail them today. I just want to finish with the list of all the major contributors, mostly 30 major contributors, and these days we are only 5 working on the tool, but there have been a lot of great contributors. Thank you.
Thank you, David. We have time for some questions. There's a microphone here coming around. Katarina.
Thank you. I was wondering, so you have this intermediate representation where all these languages are compiled to, but how do you then report the errors back to the user? What goes into that?
Yeah, so each signal will have its own notion of report. Of course, during the compilation, we take care of program locations. That are really generally attached to names. There is a risk that sometimes some messages could not be attached to the right names, of course. But for me, location is not the worst. It's most that sometimes your front end will introduce new names. I did not mention that, but we rely a lot on other representation like bytecode representations. For example, we rely on the Python bytecode, we rely on the Java bytecode. These days we rely on the LLVM bitcode. So the risk here is you will mention names that only make sense in this lowest level representation. But if your toolchain is well engineering, there should be a way to understand if this name has been synthesized by the first compiler, So you can filter which name is really a source name or an intermediate name. And also in some situations, we try to recover a bit of this information. For example, we have a way to decompile, it's a best effort approach, to decompile a bit some names to give a name that has more meaning for the developer. So it's not perfect, for sure. But yeah, I mean, in some situations, there is a signals. It's not super easy for the user to read it, but maybe it will be enough because it's already a bug and the user will understand where it is.
Okay, thank you.
Okay. There's another question over there.
Hi, thanks for talk. So you tell us your analysis is mostly used on diff. Could you tell us a bit more? Maybe I imagine there are some caching systems or the kind of information you keep, how you disable it, enable it, this kind of thing.
Yes, so we also try, so in a sense, for me, there are three and now four scenarios now where we want to use Infer. First, at IDE time, we're nice to use Infer. It's also something we already do, but we have to limit a lot the exploration depth. So it means we will not give to the analysis a lot of dependencies. So they will have to skip a lot of calls with this modular approach. But we already do that because, of course, people want to have instantaneous signals. Not that easy with an interprocedural analysis, honestly. Then we have this diff time approach, pull request, and we have what we call a conscan approach, where regularly we run Infer on all the code base. In the past, there was a kind of incremental approach where we was trying to reuse the previous analysis result on a previous version of the code. But currently, we don't use that anymore. It's a great idea, but not so easy to maintain and adapt to every new languages. Would be great to reactivate that work. I think it's very valuable. And we just use a huge amount of resource we have to run massive parallel computation, few hours. But there is also a risk that you will report bugs that was already there in the past. So we also use a heuristic to filter bugs that were already shown before. It's something that where we need also to be good at. And the fourth notion now is AI, because we want AI tool to be able to run Infer themselves. So for me, it's also a new surface. We want to make sure that this tool will know how to run Infer. They will know how to read Infer messages, and probably we will need to tell them something a bit new because they are capable of reading far more details than human. So we are also trying to adapt to that currently.
Thanks for the talk. I was wondering, how do you deal with exception?
Yeah, so in the intermediate representation I've shown, exceptions are still in the language. So there is a notion of handlers. The notion of handler for exception is quite well known, for example, in Java bytecode. There is a clear semantics for that. We use exactly the same. Then you have to decide if your analysis want to take that into account or not, because there is a risk also again of false positive. So it depends a bit. But for example, we have some resource analysis where we try to find bugs where resources were not properly closed, like opening a file. And for this specific approach, you really want to care about exceptions. So here we take them into account nicely. In Java, for example, we do that. Yeah.
Thank you.
Good. Thank you. In the interest of time, I think we have to move on. But let's thank David once more for a very interesting talk.